few general announcements. My secretary is in a state of panic. And the reason for this is since not a single student here has registered in Flex Now for this class. Although we have now this electronic platform for this class and course material and so on, it does not free you from the requirement of registering. We will today still talk a little bit about cuprates and then move on to organozinc and organoboron compounds, and will more or less finish this organometallic part quite soon. The reason is I should also announce that we will have a guest lecturer from Arkansas Fayetteville by the end of May, and he will give you a talk on sigmatropic rearrangements. And we have to make sure that we have covered Woodward-Hoffmann rules and cycloadditions before this, so we will try to focus this a little bit. So with this, you will get a real native American speaker who then can show you how it would be in the US world to give a lecture, and you can see the comparison. I'm sure language-wise it will be better. It will be also a lot faster. I can promise you this already because I know the person who is coming here. So let's talk a little bit on cuprates, and let's talk about reactions. Last time we put down 3 ways to make cuprates, 3 different types of cuprates. Now let's talk about what we can do with them. And one of the decisive features or distinctive features of cuprates is that they will readily undergo substitution reactions with a broad variety of halides, alkyl, alkenyl, and also aryl halides. And although we talked a little that organolithium compounds can also do these type of coupling coupling reactions, nevertheless, the way you can apply cuprates for such substitution reaction is much more general and broader, and that gives them distinctively different features than you would expect from alkyl lithium or magnesium compounds. And so let's simply look at a few substitution reactions, and more of them are even in the handouts. I will not show you all. But if we start with the Gilman cuprates, we looked at last time already, we talked about how to prepare them with primary alkyl halides. They will do readily substitution reactions in a way which you can formulate, and we will talk a little bit more in detail in just a second on the mechanism, but the reaction products are the ones you would expect from reacting a nucleophile with an electrophile in substitution type reactions. And so basically these reactions resemble, at least from the products, they resemble SN2 reactions. But we will see just in a moment that there is at least another mechanistic alternative there, how these reactions take place, which will not be an SN2 type mechanism. So these type of reactions work very well And of course, this allows you to do coupling reactions between sp3 centers here, and also sp3, sp2, and sp3, sp centers here. If you go to a little bit different halides, secondary alkyl halides, you will see that, or you will find out that Gilman cuprates are not reactive enough to do secondary alkyl halides. If you want to do these, you have to use the higher order cuprates. The example I have here is the higher order cuprate, which has a vinyl group in there. Higher order cuprates were the ones which you would create by the 2 equivalents of the organolithium compound together with copper cyanide. And this type of cuprate will also react with the less reactive secondary alkyl halides. And again, in a typical SN2 type fashion, at least what the products, how the products look like, you are able to do these type of substitution reactions here with the with this carbanion substituent here. Now again, keep in mind that these type of cuprates, both of them, will transfer only one group into the product. We talked about this. You need to use 2 equivalents of your alkyl lithium compound, but nevertheless, only one group is then reactive enough to undergo the substitution, while once after you have exchanged one group, the second one will not transfer any longer. And the way out to overcome this problem at least if it comes to the fact that you have a very valuable residue you would like to transfer and you would not like to lose 50%, was to use dummy ligands. And I showed you the last time an example for a cuprate preparation with a dummy ligand of the Gilman type. Let me just show you once how you can do the same thing with the higher order cuprates. So typically, one very fashionable dummy ligand is thiophene. If you metallate thiophene, you will first get the lithium compound, again assisted by the heteroatom, so selective lithiation next to the heteroatom will take place. And then in the next step, what you have to do is you add copper cyanide And this will do the transmetallation to give you this type of salt. And now if you treat this with your alkyl lithium or organolithium compound, which contains the residue you would like to transfer, you will now create the higher order cuprate, the mixed one. Which we can represent with a formula which looks like this. And again, I would like to stress that the real formula, the real structure of these molecules are much more complex. Usually these are dimers or even oligomers. And more or less what we do here is we're representing the stoichiometric formula, but the real structure might be very different here. Now again, here you are now in the situation that you have your dummy ligand here. Which will not transfer into the product. It will not undergo a reaction with the electrophile you offer. And let me take the example here. Let me use a slightly different electrophile in epoxide. And again, ring opening reactions with epoxides with cuprates works very, very well. Again, you can think of this as a SN2 type reaction. Usually you attack the sterically less hindered face or less hindered side of this epoxide. And so in this case, what you obtain in good yields, this example has been reported, a 73% yield is the ring opening product where you selectively have transferred the vinyl group, not the thiophene group. And again, here, of course, you only need to use one equivalent. So again, that's the dummy strategy. So let's look at a few more reactions. So let's look at another substrate. This dibromocyclopropane, quite readily available by a cyclopropanation method where you would use cyclohexene, bromoform, sodium hydroxide in order to create the dibromocarbene, and you would use a phase transfer catalyst like an tetrabutyl alkyl halide in order to mediate between the organic phase and the aqueous phase, typical phase transfer catalyst. in order to create or be able that the aqueous sodium hydroxide can react with the organic alkyl halide here. So this way you can create very easily such cyclopropane adducts. And now if you react this with the cuprate, for example, this Gilman cuprate, in a very clean reaction, you will exchange the bromides for the methyl group. This should already start the question, is this still an SN2 type reaction? Because usually in an SN2 type, SN2 reaction, you have to be able to do an inversion of your electrophilic center here. So the nucleophile attacks and then inversion takes place. And of course, in this three-membered ring, such an inversion process is not possible. Let's look at a second example here. Also very well established are reactions in which you would react a vinyl bromide. So again, same idea. Reacted with a cuprate. And again, in a very clean and high-yielding reaction, 95% yield. Quantitatively, this reaction was reported with 65% yield, still very decent. This reaction, these type of substitutions take place. And again, this looks like now like a formal substitution on an sp2 center, right? And we know on sp2 centers all we do are additions in the first step, or we do not really do substitutions. And let me just put on the board one more example, and then we talk about the mechanism. Take this vinyl iodide here. The reason I put this on is you can see that we have here hydroxyl groups, which normally you would not think to do reactions, organometallic reactions with free hydroxyl substituents. Cuprates tolerate this. And so again, in a very clean coupling reaction, this iodine atom could be exchanged for this ethyl substituent here. So again, it looks like we have done a substitution reaction on an sp2 center, and that is, of course, something you would not think would be a reasonable mechanistic proposal. So in principle, what have been put forward are two different proposals for mechanisms how cuprates can react with halides. And the one reaction, indeed, is the direct nucleophilic displacement, the same way as you would propose it for a nucleophile reacting with an alkyl halide. The reaction would go with inversion. But the other proposal, which is probably operating when you do the substitutions on these sp2 centers, so this here would be more probably a typical proposal which might be valid for the sp3 centers, but for sure for the sp2 centers, it's believed that an oxidative addition takes place. And this is a very common elementary step for transition metal type chemistry. What is happening here, we are on copper in the oxidation state of +1. And what is now believed is that the cuprate, the copper, can oxidatively insert between the carbon and the halide bond. And this way, you would form a copper intermediate which has the oxidative state, the formal oxidative state, I should say probably more precisely, of +3. So therefore, you have oxidized the copper from 1 to 3. And this is why this is called an oxidative addition. And this type of elementary step we will see extensively when we will discuss palladium catalyzed cross-coupling reactions, because this type of reaction always takes place. So again, it's believed that this takes place with inversion. So stereochemically, you do not see a difference between these two types of reaction mechanisms. And from this species, I can actually go directly to here. What will be happening is a so-called reductive elimination. So this R group is migrating to the center here, and the copper fragment gets extruded, thereby regenerating, again, copper in the oxidative state of +1 and forming the product here. And again, in palladium chemistry, we will see this type of mechanism, oxidative additions, reductive eliminations, drive many very useful reactions. Now let's look at another reaction. Let's take an example how cuprates will react with acid chlorides. And again, in a very selective way, you are able to convert an acid chloride to the corresponding ketone here, where again we have introduced one alkyl group from the cuprate here into the product. And keep in mind the difference if you would have tried this with an organolithium compound or an organomagnesium compound. Although again you go from the more reactive to the less reactive carbonyl derivative, but with an organolithium or organomagnesium compound it would have been extremely difficult to stop that reaction at the ketone stage. With the cuprates, this is not a problem. Ketones will not react. Ketones will not add cuprates to the carbonyl group, and so therefore you have a very powerful way to do these type of transformations. Now there's a very interesting aspect of this. And this is if you prepare cuprates not via the organolithium compounds, but if you prepare this via the organomagnesium compounds, then the big advantage is that only catalytic amounts of copper salts are needed any longer. So in difference to the organolithium compounds where you would stoichiometrically take the organolithium compound and one equivalent of your copper salt to make the cuprate, if you start from Grignards, it has been shown that you can actually do this in situ. So you can take, and I show you immediately an example for this. Which should show you the potential. If you have this compound, which contains an acid chloride group and an ester group, if you would react this with the Grignard compound, the Grignard should react with the acid chloride. As we discussed, it probably should add twice on the acid chloride. But still, even with this ester here, the reactivity of the Grignard is sufficient to also add to the ester group. However, it's now sufficient to have catalytic amounts of copper iodide, typically like 20 mol% copper iodide present. So you take this compound, you mix it with copper iodide, and then you slowly add the Grignard. And what is happening is that this transmetallation from the Grignard to the cuprate is so fast, it's much faster than the reaction with your carbonyl compounds here. And then the cuprate will not react with the ester. It will only react with the acid chloride. So indeed, in very good yields, the product you would obtain here is the alkylated acid chloride, leaving your ester group alone, but you also do not observe the twofold addition product. And you can see here this reaction was reported with 86% yield, so almost quantitatively you can probably get a feeling that these processes are very, very efficient. And so again, something we talked about when we talked about the organolithium compounds, these transmetallation steps are extremely fast. And you see that they can very successfully compete against electrophiles, where in principle this Grignard reagent also should react with. And so there are many, many examples of this type, and you have some more examples in the handouts. You have also some more details in there, what kind of solvents are being typically used I do not want you to memorize these details. If you look through the handouts, read through it, again, get a feeling for this, but it's certainly not important to memorize now which solvent and which type of conditions you should use, but you should understand this general type of reactivity pattern which we have been discussing here. Let's take another example which will have some stereochemistry in there. And it will also give you a new reaction type, which I would like to discuss now. And these are conjugate additions. Now, in this example, you have an alpha-beta unsaturated ketone. So in principle, you have two possibilities for a nucleophile to attack. So nucleophile could attack here, or nucleophile could attack here. Now, one very important feature of the cuprates is that in the terms of hardness and softness, cuprates are much more covalent. They are not as ionic as organolithium or organomagnesium compounds. Therefore, they are representing soft carbanion equivalents. And in a situation like this, again, these two centers where the nucleophile could attack differ in their hardness. The center which is attached directly to the carbonyl oxygen, because it feels particularly strongly the electron withdrawing power of that atom, is a hard center, while this center here is not as polarized as the other atom, and so this is a soft center here. And again, cuprates more covalent are classified as soft. While alkyl lithium or Grignard reagents are typically hard reagents. And so in a scenario like this, you can, by the choice of your reagent, you can either attack the nucleophile on that carbonyl center. Since it's a hard center, you have to react it with a hard reagent, so you would take an organolithium or an organomagnesium compound. If you want the reaction on this center, which is called a conjugate addition, you would use the soft cuprate here. So this is a very general feature, that these conjugate additions are always almost exclusively being accomplished by cuprate additions. What did we react it with? The example I have here is again a Gilman cuprate. So introduction of a methyl group here on this center. So note that there's a new stereocenter here, which is being formed here, and the reaction is taking place completely diastereoselectively. And let's look at this example to understand how selectivity, especially in such cyclohexane systems, can be understood. If I draw already the saturated system here, and draw in the cyclohexanone, and you know that that this is of course more the saturated representation. The angles are more open when you have a double bond in here, so it's more a half chair type. But in principle, in order to understand this, giving such a representation is a good idea. And now let's see that we did this right. The methyl group is pointing down here, and the hydrogen atom is pointing down. So this is, we have a cis junction. These two substituents have to be on the same side, and they're pointing down in the exact same way as we have drawn it. Now, since we have the pi system here, the pi system, and more specifically the pi star orbital, has to be attacked by the nucleophile. And this is indeed accomplished in a chair. We can attack equatorial or axial. And in this type of scenario, the axial attack will be most suitably oriented in order to interact with the pi star orbital. So the attack will come from this side, and this will also allow, and this is a very important principle, that the bond reorganization has to be minimal, because once we add here, you can see I have already drawn it in that saturated situation. So if I do the axial attack here, then my six-membered ring, which was before in the cyclohexene state a little bit more flat, has to reorient only very little. While if we would have tried to do some kind of an equatorial attack, we actually would have had to flip the ring here. And so this is the driving force here, has been also been put a name to. That's the principle of least motion, meaning that atoms, like humans, would like to, if the reaction takes place, would like to do as little work as possible. And so therefore the trajectory in which you do not have to do a lot of reorganization of your bonds is favored. Now note here that in this bicyclic system, we have, in general, two different phases. Any attack from above here would be within this shaped cycle. So if we look at this molecule looks more or less like this. It's like a cup, and it has concave phase, and it has a convex phase. And a very strong driving force is that concave phases are sterically very encumbered, and therefore reactions like to attack from the sterically much less hindered convex phase. And this is also realized here. Now I could have flipped the ring. Let's do this. If I flip this bicyclic system, And note these beautiful chairs. Since last lecture, the one chair really was not very well drawn. All day long, I improved my chair writing. So try something like this when you are in a boring seminar or so as well. See if you can write nice chairs. And so again, I give you already the representation, although I'm aware that the cyclohexanone is not really in a chair type orientation like this, but that it is more distorted. And also note that I flipped it and then I moved the carbonyl group again one down in order to put the other chair down here. So again, in this scenario, the preferred attack would have come from this side, again in order to attack the double bond in a way that the chair is basically already in the right conformation. But now you see this would lead to the product where the methyl group is opposite to this methyl group. But now you see that in this case it would attack from the concave face, and that is not this is not favored. So in this case, attack comes from here, from the same face like the methyl group is on. And so therefore, we would conclude, and indeed this is the only product you observe, that the correct stoichiochemistry is the product which contains the methyl group in the cis orientation to this methyl group. So again, this is something I believe we will encounter a couple of times again, and one has to practice this type of analysis. But I hope more and more you will also get the feeling not only for the reactivity issues, but also for selectivity issues, and then make reasonable assumptions what product should be preferred and which one is the less preferred one. So let's have a brief look at the mechanism of these conjugate additions. In principle, of course, it's a nucleophilic attack onto the center. But again, it's commonly believed that some similar type, as we have seen before, again involving a oxidative addition will take place. Believe that the copper fragment will coordinate to the double bond, which is assisted that the Lewis acidic lithium, which is of course also present in the cuprate, will coordinate to the oxygen compound here, and therefore pulling out electron density from this double bond, allowing this type of coordination here. And then again, it's believed that copper will do the addition, again being an oxidative addition, going from the reaction state +1 going to the oxidative state +3. Again, might be an organic look of view. There's good evidence that there are copper-3 intermediates. If you ask our inorganic colleagues, they have their doubts when it comes to copper-3. Nevertheless, in this formulation, now we would propose after the oxidative addition the reductive elimination which now would lead to the transfer of one of the alkyl groups from the cuprate into the product. Now note that you are getting an enolate here, a lithium enolate in this type of reaction. And this is, of course, a very useful synton. In the easiest way, or in the simplest way, you would work it up with water. Then you get the ketone back here and simply the normal 1,4 addition where you only have added your nucleophile to the double bond. However, you can now use a second electrophile. And such an electrophile does not have to be necessarily a proton. It can be an alkyl halide. Alkyl iodides are particularly good for this. It can be a carbonyl compound, for example. And then this way, you would not only have introduced the nucleophile from the cuprate, but at the same time, you would have functionalized the double bond. In addition, with an electrophile, you can bring in as a second step. That, of course, again gives you added power in these type of reactions. So this was the conjugate addition to alkenes. How about alkynes? And alkynes react in a very interesting way with cuprates. And again, let me give you an example right away. So while in the conjugate addition to a double bond, you need an electron withdrawing substituent, cuprates will actually add also to simple alkynes where you do not require the electrophilic substituent. And so in this case, syn addition will take place. In that one group will be transferred to one end of the triple bond, and then the copper fragment, which still bears the other alkyl substituent we had initially in here, is adding to the other fragment. If I want to make it stoichiometrically correct, and this would be a suitable representation. Now, after you've done this, you have created a second cuprate again. And that makes it interesting because in a scenario like this, the vinyl groups are more reactive than the alkyl groups. So although, in principle, if you would now react this with another electrophile, either the alkyl group or the vinyl group could be transferred. In reality, the vinyl groups react much faster. And so, for example, now you can add a second electrophile. The example I have here is again an alkyne, this time having an electron withdrawing substituent. And what will happen is that another syn addition takes place. Basically giving you an intermediate like this. And such vinyl cuprates now, in the easiest way, again, you can hydrolyze them, let's say with water, acid. This hydrolysis, again, probably goes through a reductive elimination mechanism. A proton coordinates to the copper, and then reductive elimination to the carbon center, and extruding the copper is going to take place. Oops. So again, if I want to make this stoichiometrically correct, this should be an ionic species. This should be with a lithium countercation. So as you can see here, in these type of reactions, look what you started with. You started with your alkyl lithium cuprate. Then you have been able to introduce normal acetylene. Then you were able to introduce a second acetylene. So in a more or less one-pot reaction, you have assembled quite a lot of useful functionality here, and being able to build up carbon structures quite rapidly. Now, the protonation here is probably the most boring, but nevertheless, of course, important alternative or workup you have. Let's take another example. So let's take the isopropyl cuprate, obviously in this case, which was prepared from isopropyl magnesium bromide. Reacted with 1-hexene. And again, as syn addition takes place, which we can formulate like this. Now note that a difference to this example, now my alkyne here is unsymmetrical. So a regioselectivity question comes. Should the isopropyl group react on this center, or should the isopropyl group react here, and where is the copper going? And again, very often in these type of scenarios you get mixtures. However, as a general rule, you can assume that the copper fragment, which is doing the initial addition, having all these isopropyl groups still on it, and then only afterwards the reductive elimination will take place, that the copper fragment is the sterically larger group. And therefore, this should add at the sterically less hindered side. So the addition the initial addition of this fragment is taking place, and I think it becomes clear that the least steric hindrance, the more favorable that attack should be. So then you have these type of vinyl cuprates here. We already said we can hydrolyze it, but we can do other things. With this chlorocyane, for example, you can react it, which then will introduce a cyanoelectrophile in this case. Giving you this nitrile. Now note that all these type of hydrolysis reactions, this reductive elimination mechanism, some electrophile is coordinating here and then migrates to the carbon center. They always occur under retention of configuration, which I believe if you just simply draw the mechanism becomes intuitive, and indeed this is always what is being observed in these type of reactions. Or you can add other electrophiles. Let's take allyl bromide here and transform your cuprate into the allylated compound. And these are very good reactions, usually very high yielding, and therefore, as you can see, from very easy, readily available building blocks, you can actually build up more complex structures quite rapidly. Now note again here that the isopropyl group, the alkyl group, is apparently not transferring very easily here. You do not observe the twofold addition product here, but you have to add another electrophile and then a more reactive electrophile, which then will preferentially transfer again over the alkyl group. Okay, so this is what I wanted to tell you about cuprates. There are many, many more aspects. You could have a whole lecture just on cuprates, but I hope it gave you a feeling what these type of reagents can actually do. I want to touch very briefly organozinc compounds. Which are in many ways similar to cuprates. They are also quite covalent organometallic species in difference to the organolithium and organomagnesium compounds, which are more ionic. They undergo coupling reactions similar as we have seen from the cuprates. Let me just give you one example for this. So again, organozinc compounds you can either prepare from organolithium or organomagnesium compounds by transmetallation with zinc chloride, for example. However, if you have highly activated zinc metal, analogous like a Grignard reaction will take place. Also, the organozinc, the zincation will take place. However, you cannot just take normal zinc powder out of the bottle because that contains a lot of oxides. Usually, what you have to do is you have to start from anhydrous zinc chloride and reduce it, for example, with magnesium. We talked already on this Rieke variant, where by the reduction now you will form very active zinc powder and magnesium chloride. And this way you have quite a convenient way to do this. The other way, quite common reagent, is the zinc copper couple, where you form an alloy between zinc and copper, and that also greatly activates. If you simply mix zinc powder and copper powder, and there are special procedures to do this, this will also give you an activated zinc metal. Activated enough in order to allow to form an analogous Grignard compound, in this case the organozinc iodide. And now if you react this with a suitable coupling partner, where I've been choosing this iodide, now again, since these reagents are much more covalent, they will not react with carbonyl groups. Think again about this. If this would be an organomagnesium compound, this would immediately react with the carbonyl compound. Now the zinc compound, and what is almost always being done in this case is you add copper cyanide and lithium chloride to this. So again, you form some kind of analogous zinc, organozinc cuprate species, which has some, probably again, some lithium inside there as well. Again, the structures are not very clear at this point. However, then in this case, exclusively the formal substitution with the alkyl halide will take place. And there will be, like in this case, there will be no carbonyl addition here. The one thing, again, from the mechanism, it could be an oxidative addition mechanism, which we have earlier postulated. However, with these alpha-beta unsaturated carbonyl compounds, which have a leaving group here, you always have also the possibility as a mechanistic proposal that you do the addition and then the enolate might, upon workup, might actually form back here the double bond by elimination under the workup conditions of HI here. The two reactions which you should remember, which are more or less unique to organozinc reagents, is the Reformatsky reaction, which I will introduce now, and then in just a moment I will show you a second reaction. The Reformatsky reaction starts from alpha bromo esters, which are very easily available by bromination of the corresponding esters. You go through the enolates, can very readily prepare such alpha brominated carboxylic ester compounds. And it has been found that with this activated zinc metal, you can quite readily obtain such alpha zinc ester species. Which are probably in equilibrium with a simple enolate. So basically it's an alternative way to make a metal enolate here. And then these type of intermediates will rapidly react with all kinds of carbonyl compounds. Which will lead to the normal addition products. The way this works very well is that there is most certainly coordination of the zinc atom with the two oxygen functionalities here. This type of motif we will see again when we talk a little bit closer about aldol reactions. And then after workup, you have formed the addition product here. This reaction is particularly useful because these type of reagents are so readily available. And as you can see here, in difference to normal enolate chemistry, you do not have to use a base here. There's no base involved. There's only the basically metal in addition to the carbon halogen bond here, which then is an equivalent for the corresponding enolate. Moving these boards is counterintuitive. Whoever did this was not doing this because the board in the back is being moved by the buttons on top. And although I'm doing this now for 6 years or 7 years, I cannot get used to it. The second reaction, and that is probably the even more important reaction because there are less alternatives for this, is the so-called Simmons-Smith reaction. And this is a reaction where you start from diodomethane. And again, treating this, I just write zinc, but keep in mind it has to be this type of activated zinc. Treating this with zinc, you will form an organozinc compound, which is generally accepted to be formulated like this. Again, the actual structure is probably more complicated. And so this is the Simmons-Smith reagent. There's a second way to generate a very similar species, which will do the same chemistry. And this is if you treat diiodomethane with diethyl zinc, which is commercially available, you will form something analogous, which I will which you can formulate like this. And this has been known as the Furukawa reagent. It does the same chemistry as we will see in a moment, like the Simmons-Smith reagent is doing, but very often it's more convenient to prepare it this way, because you can take diethyl zinc out of the bottle, diiodomethane out of the bottle, but here you have to generate your activated zinc first. And so both of these reagents will react with double bonds in a cyclopropanation reaction. This is why this reaction is so important, because there are not so many alternatives. And so in principle, you can think of this reagent as an equivalent of carbene. However, it is known, although formally you can eliminate here, of course, immediately zinc iodide to generate carbene here, it's known that the reaction mechanism, if you react this with alkenes, there are no free carbenes present. Everything goes through this type of methyl species. So a transition state you see very often in the books is being proposed as looking somehow like this. We're now in the course of the bond formation between your carbon fragment and the double bond centers. This elimination of zinc iodide will take place. And so the overall outcome is indeed that you form the cyclopropane adduct plus zinc iodide. But again, it's not an addition of a free carbene. It goes through some kind of an organometal intermediate like this. This is a very useful, very broadly applicable reaction. And let me give you one more example, which will illustrate an important feature of this reaction, and that is that it will not only cyclopropanate double bonds, but when you have a heteroatom, especially when you have an alkoxy functionality in your molecule, what will happen is that the zinc will coordinate to this oxygen it will pre-coordinate, and therefore the oxygen atom will direct the carbene to the double bond. And this means if this oxygen is looking up, then the substituent looking up or going in front will direct the carbene to the front side of the double bond rather than to the back side. So reactions like this are highly diastereoselective. We can draw some kind of a transition state to make this again plausible. Let me this time draw the cyclohexene ring as you would normally do this in this type of half-chair representation. You have now your alkoxy group in a pseudo-equatorial position. And the zinc will pre-coordinate maybe and now the bond reorganization will take place. You might want to formulate this like this. I'm missing one iodine still here. And so the outcome in this case is that you will have formed only one diastereomer. The other possibility where the carbene would have been delivered from the bottom phase, which you would think rightly is the sterically least favored site in this case, right? Because the alkoxy group, of course, would shield this. But because that pre-organization, that pre-coordination takes place, this product here is not formed. And this is here the only one which is observed. This type of strategy where you have directing groups here and these reactions are called directed reactions. And there are many, many, especially when you have organometallic reactions. Many times heteroatoms will pre-coordinate with that transition metal or metal and then deliver this way a reagent selectively to the to one phase over the other in a molecule. These type of directed reactions have become extremely important because they are usually more selective than if you have to differentiate based on steric hindrance. And so these directing groups very often are also called active volumes in difference to if you would have a situation where you would have a sterically large group which would simply shield one side, which then would be, is often called a passive volume. And so, principle what this should mean here is that sometimes you can have directing effects based on shielding, on the passive presence of that substituent, or the substituent can be actively involved into directing the reaction. Okay, with this we will finish the organozinc compounds. We didn't start as I wanted with the organoboron compounds, but this will be also relatively brief. And with this I wish you a nice weekend. Tutorial 3 is on the web. It's only 3 questions. Please have a look at this so that we can discuss this a little bit on Monday together. Have a nice weekend. Lots of time to look in the tutorial because the weather will be very bad, I heard. So no excuses. See you on Monday.